In this video, we'll be going through question 14 from the 2024 HSC Mathematics Extension 2 exam. Part A. Prove that if a is any odd integer, then a squared minus 1 is divisible by 8. So if a is an odd integer, we can say if a is odd, then a will be equal to 2k plus 1 for some integer k. So this means I can write a squared minus 1 as 2k plus 1 squared minus 1. Let's expand this out. We'll get 4k squared plus 4k plus 1 minus 1. The plus 1 and minus 1 will cancel, and I'm going to factorize, and I'll get 4k outside of k plus 1. Now I'm trying to show that it's divisible by 8, which means I'd like to show that this expression is equal to 8 times some integer. This expression here. Now I already have a factor of 4 sitting at the front, so somehow there's a factor of 2 hidden within this expression, k times k plus 1. And I need to justify why that's the case, or how that's the case. And the reason is, well, these two are consecutive integers, so one of them has to be odd and one of them has to be even. And if one of them's even, that means that has a factor of 2 hidden within it. And then I'll have 2 times 4, which gives me 8. So I'll justify it by writing out what we just said. Okay, so we've got that since k and k plus 1 are consecutive integers, one of them must be odd while the other is even, which means their product is the product of an even with an odd, which is an even number. So it's equal to 2m. So now I can say that a squared minus 1 equals 4 times 2m. I should have said here where m is an integer, because I need that. M is an integer. And so this is equal to 8m, where m is an integer. And so therefore, we've got that a squared minus 1 is divisible by 8. And that's the end of our proof. Part B. Use mathematical induction to prove that 2n choose n is less than 2 to the power 2n minus 2 for all integers n greater than or equal to 5. Okay, so we're going to start off with our base case, and that's when n is equal to 5. Our left-hand side will be equal to 10 choose 5, and simply punching that into the calculator tells us that this is equal to 252. And the right-hand side, well, that's equal to 2 to the power 2 times 5 minus 2, which is 2 to the power 8. Again, you can put that in your calculator, or you might just know that that's equal to 256. And so clearly, my left-hand side is less than my right-hand side, and so therefore it's true for the value n equal to 5 for our base case. Now I need to make my inductive assumption. So I'm going to assume for some value of k that's greater than or equal to 5, and it's important that I specify what range of values k can take. And in some questions, it's actually very important because it helps you to complete the proof. But certainly if k is going to be greater than or equal to 5, if n is greater than or equal to 5, then this k ought to be greater than or equal to 5 as well, because this is a number that n can take. So I assume for some k greater than or equal to 5, that we have 2k choose k is less than 2 to the 2k minus 2. And I'm going to label this assumption here because I know eventually I have to refer to it. Otherwise, I wouldn't be doing mathematical induction, I'd be doing something else. So I'm going to label it so when it comes time, I can just say by the start equation. Now, what would I like to prove? I'd like to prove the truth of the statement for n equal to k plus 1. So I'm required to prove that 2 times k plus 1 choose k plus 1 is less than 2 to the 2 times, that should be k plus 1 minus 2. Okay, in other words, it might be useful to write this as an equivalent statement. We're trying to prove 2k plus 2 choose k plus 1 is less than 2 to the power 2k, after just simplifying a little bit both sides. Okay, so let's have a look at the left-hand side. Our left-hand side is 2k plus 2 choose k plus 1. And I'm going to write this in its factorial definition. So this is 2k plus 2 factorial divided by k plus 1 factorial, and then I have 2k plus 2 minus k plus 1 factorial. Okay, let's simplify things. We have 2k plus 2 factorial, then I have a k plus 1 factorial, and this second bracket here is actually also going to be k plus 1 factorial. Alright, now if we have a look at what we have in our assumption, we have 2k choose k, and if I write this on the side, 2k choose k, if I write that in its factorial definition, that's 2k factorial times k factorial k factorial. So I'm going to factor out a couple of terms from each of this factorial so that this expression appears. So in the numerator, I'm going to factor out 2k plus 2 and 2k plus 1, and then I'll be left with a 2k factorial. And in the denominator, I'll factor out a k plus 1 from each of those factorials. So I'll get k plus 1 squared times k factorial squared. Okay, now we're going to do a bit of simplifying. Firstly, I can factor out a 2 from this 2k plus 2, and I'll get 2 times k plus 1, and then this k plus 1 factor will cancel with one of these in the denominator. So I'll end up with 2 times 2k plus 1 divided by k plus 1. And then I'm going to write these three terms, which I'm actually going to highlight here. Those three terms. I say 3 because there's really a k plus 1 k factorial squared there. I'm going to write this, the highlighted part, as being 2k choose k. Okay, that's coming from what I've got over here. And now I'll be able to use my assumption on this. So I'll say that this is less than 2 times 2k plus 1 over k plus 1 times, from the assumption, it will be less than 2 to the power 2k minus 2. I'm using my assumption, so I'm going to reference it by star. And now I just have to make my way down and try to land at 2 to the power 2k. So I really need to somehow turn this into 2 squared. Well, I've already got one of the 2's that I can combine with this 2 to the 2k minus 2. So let me do that. 2k plus 1 over k plus 1. 2 to the 2k minus 1. And now I'm going to claim that this is smaller than 2k plus 2 over k plus 1. And the reason I want to do that is because I would be able, if this was a 2, to factor out a 2. And the k plus 1 would cancel with that k plus 1. So the claim is that this is less than 2k plus 2 over k plus 1 times 2 to the k minus 1. Of course, this fraction now is simply equal to 2. So that's 2 times 2 to the 2k minus 1. And that's equal to 2 to the power 2k. And that's equal to the right-hand side. So I've shown that my left-hand side is less than the right-hand side if the assumption is true. And so therefore, by the principle of mathematical induction, I'll just abbreviate to MI, the statement is true for n greater than or equal to 5. And that is the end of part B. Part C says, for the complex numbers z and w, it is known that the arg of z divided by w is equal to minus pi on 2. Find the modulus of z minus w over z plus w. Now, if we know that the arg of z divided by w equals minus pi on 2, that means the complex number z on w has to lie on the negative part of the imaginary axis. So if we quickly draw up an arcane diagram just to convince ourselves of this, if I go negative pi on 2, travel to negative pi on 2, I land on this part of the axis, of the imaginary axis. So what that means then, I can say that the arc of z on w equal to minus pi on 2, that tells me that this number z on w should be purely imaginary, but it should have a negative component. The imaginary component should be negative. So it should be equal to minus ki, where k is greater than 0. Now what does that mean? That means I can write z as minus kwi. And I'm going to substitute that back in to the expression that we're trying to evaluate. So I'm trying to find the modulus of z minus w on z plus w. So I have minus kwi minus w divided by minus kwi plus w. Well, I can divide top and bottom by w. I'll end up with minus ki minus 1 divided by, let's write it as 1 minus, ki. Now what I'm going to do is I'm going to factor out a negative 1 from the numerator. And then that'll get swallowed up by the modulus. And so I have 1 plus ki. And in the denominator I have 1 minus ki. Now 1 minus ki is the conjugate of the numerator, 1 plus ki. So I'm going to write this as 1 plus ki divided by the conjugate of 1 plus ki, and I'm taking the modulus of this. Well, the modulus of a quotient is the quotient of the individual moduli. So this is the modulus of 1 plus ki over the modulus of 1 plus ki bar. But a complex number and its conjugate have the same modulus. So I can write this as the modulus of 1 plus ki divided by the modulus of 1 plus ki. And that is something divided by itself, which is equal to 1. And so the value of this expression is simply equal to 1. Part D. The following argument attempts to prove that 0 equals 1. And then they present us with an argument that uses integration by parts to show that 0 equals 1, supposedly. And they want us to explain what is wrong with the argument. So here is the argument. Here is the supposed proof. They start with the integral of 1 on x dx. They write the integrand as 1 on x times 1. Use integration by parts to integrate 1 on x and to differentiate 1 on x and integrate 1. And they get down to this point here. And then they say that they're going to subtract the integral of 1 on x from both sides. And that leaves us with 0 equal to 1. And actually this is quite a subtle flaw in this proof, because up until this point here, everything is fine. The issue comes in the very last step. And the issue is that these two integrals here are not actually the same thing, because they have different constants of integration. So I'm going to call this line here star, so I can refer to it. Now obviously in an exam you'd probably have to write at the line blah blah blah, but because I was able to screenshot it, I'm just going to call it star. So inline star, the left hand side and right hand side both have this integral, the integral of 1 on x dx. However, they do not necessarily have the same constant of integration. So when I subtract an integral from both sides, I have to make sure that they'll have the same constant of integration. And here they're not going to have the same constant of integration. In fact, the constant of integration is going to differ precisely by 1. And so therefore, we have subtracted different values from both sides. leading to 0 equal to 1. Okay, and that's the end of part D. Part E. The diagram shows triangle OQA. The point P lies on OA so that OP to OA equals 3 to 5. The point B lies on OQ so that OB to OQ equals 1 to 3. The point R is the intersection of AB and PQ. The point T is chosen on AQ so that OR and T are collinear. Let A be equal to OA, B equal to OB, and PR equal to KPQ, where K is a real number. Part I says to show that OR equals 3 on 5 into 1 minus K times A plus 3K times B. So I'm trying to find an expression for OR, which is this vector here. And I've been given these ratios. I've also been given that the vector OA is equal to B. So I'm going to add that in. So there's the vector OA, and that's equal to A. Now if this is equal to A, then OP, which is 3/5 as long as OA, is going to be 3 on 5. So I'm just going to write here that this is 3 on 5A. Similarly, we have OB. OB is equal to the vector B. So let's draw that in. And that tells me that OQ is going to be 3B. I'm not going to write it in, but I'll just keep it in mind. Now I'm trying to get the vector OR. So I can see that OR is equal to OP plus PR. Now OP, well, I know that that's equal to 3 on 5 lots of A. What's PR? We're told in the question that PR is equal to K times PQ. But I can get from P to Q by going from P to O and then from O to Q. And that's a path that travels along vectors involving A and B. So I'll say that this is equal to 3/5 times A plus K into negative 3 on 5A plus, we said OQ was equal to 3OQ, so that means it's equal to 3B. And now just collecting the A's and the B's together, we'll get 3 on 5, 1 minus K times A plus 3KB. And that's part I done. Now part 2 says, writing AR equal to HAB, where H is a real number, it can be shown that OR equals 1 minus H lots of A plus HB. Do not prove this. And we want to show that K is equal to 1 on 6. Okay, so we get from the question, we're told that OR, or from the information given to us, we're told that OR equals 1 minus H times A plus H times B. So now I have these two expressions for OR. I can equate those. Right, I can equate these two. So, therefore, 1 minus H A plus H B is equal to 3/5 1 minus K lots of A plus 3K lots of B. And now here we'll notice that A and B are not parallel. This is A and this is B. These are not parallel vectors. And so now I can equate the coefficients of A and the coefficients of B. So I'll say since A is not parallel to B, then we have 1 minus H equals 3 on 5 into 1 minus K. We'll call that equation number 1. And we have H equals 3K. We'll call that equation number 2. I can substitute 2 into 1. And we have 1 minus 3K equals 3/5 1 minus K. Now we'll solve this for K and we should end up with 1 on 6. So I'll multiply across by 5. Expand that bracket. Bring the K's to one side. We'll get 12K. And then K is equal to 2 on 12, which is 1 on 6. And that's part 2 done. Now part 3 says, find OT in terms of A and B. So if we go to the diagram, we see that OT can be expressed as OA plus AT. And I know what OA is, that's equal to A, obviously. And AT, however, that can be written as the scalar multiple of AQ. So that's a few things in one. Let's take it one step at a time. We'll say that OT equals OA plus AT. OA, of course, is equal to A. And AT will say that that's mu, some scalar, times AQ, where mu is a real number. Okay, but AQ, I can express that in terms of A and B. That's simply traveling along negative A plus 3B. So I'll write that in. I've got this as A plus mu negative A plus 3B. Let's collect the A's and the B's. So 1 minus mu A plus 3 mu B. That's my expression for OT. Okay, good. But what else do we know about OT? We know that OT is a scalar multiple of OR because they lie on the same line. So that means I can write OT as another scalar. Let's call that scalar lambda. I can write it as lambda times OR. And I actually know what OR is now because in part 2, I found the value of K to be 1 on 6. And so I can now sub that in to this expression for OR. And it should end up being, I think it looks like a half A plus a half B. So I'll say, but OT is parallel to OR. So therefore OT equals lambda OR, where lambda is a real number. Now OR is equal to 3/5 into 1 minus K, but we said that K was equal to a 1/6, plus 3 times K, B. So this is 5 on 6. 3 on 5 times 5 on 6 is 3 on 6, which is a half. So we have a half A plus a half B. So now I can substitute this expression for OR, this expression for OT, into this equation, OT equal to lambda OR. So therefore, 1 minus lambda A plus 3 mu B equals lambda into a half A plus a half B. Again, we can say since A is not parallel to B, then I'm able to equate the coefficients of A and the coefficients of B. So I have 1 minus mu equals lambda on 2, and I have 3 mu equal to lambda on 2. I can sub one into the other, I can equate them, and I'll get 1 minus mu equals 3 mu, which means mu will be equal to a quarter. So if mu is equal to a quarter, what does that mean? That means I can now sub that back into this expression, and I'll get OT in terms of A and B. So therefore, OT will be equal to 1 minus a quarter times A, plus 3 times a quarter times B. So that'll give me 3/4 A plus 3/4 B. And that is the end of part 3 and the end of the whole question.